Generative AI crashed into higher education overnight, forcing administrators into an immediate, high-stakes scramble to respond. Administrators face a very specific fear. If they simply deploy off-the-shelf chatbots, they risk handing students an automated cheating engine that bypasses actual learning. To find out if this tech could actually teach, researchers at Harvard designed a randomized controlled trial, or RCT. An RCT is a scientific study where participants are randomly assigned to different groups to measure the exact impact of a specific intervention. The trial shifted the institutional focus away from adoption toward the curriculum engineering required to force mastery. The Harvard study split a large physics course into two groups. One group received highly optimized in-person active learning. The other interacted solely with a custom-built AI tutor called PS2 Pal. This chart maps student mastery. The baseline learning gains from the in-class group set a high standard, but AI-tutored students saw test scores jump, doubling the classroom group's learning gains. The AI group achieved these superior results, spending significantly less time. Tech companies market AI as a plug-and-play solution, but Harvard's success relied on months of heavy, custom engineering, rather than a default chatbot interface. To replicate these outcomes, institutions must abandon the idea of out-of-the-box software. Real gains require rigorous, institution-level curriculum engineering. The operational engine driving Harvard's custom tutor is a technique called scaffolded prompting. Scaffolded prompting is a method of programming an AI to break down complex problems and guide users through them one sequential step at a time. An unguided commercial chatbot will simply spit out the final answer to a physics equation. A scaffolded AI refuses to give the answer, instead forcing the student to solve each part of the problem on their own. Looking at the system's architecture, designers eliminated inaccurate AI hallucinations by feeding the model expert-crafted, step-by-step solutions. This rigid structure creates a safe environment. When a student enters a wrong answer, the system redirects them, building persistence and a growth mindset. Building this architecture requires a massive investment of time. Subject matter experts must spend weeks writing specialized prompts and testing conversational pathways before a single student logs in. The institutional trade-off is clear. Eliminating digital shortcuts and ensuring academic rigor demands an intensive, mandatory upfront investment of faculty resources. This specific AI integration relies on the flipped classroom model. A flipped classroom is an instructional strategy where students first learn new content at home, freeing up actual class time for active problem solving. Under this structure, the operational flow shifts entirely. Students make their first contact with difficult new physics concepts in isolation at home, with the AI serving as their personal guide. This private environment allows diverse learners to set their own pace. It removes the friction of a one-size-fits-all lecture speed, letting advanced students move quickly, while others take the time they need to grasp the basics. By transferring baseline content delivery to a machine, human instructors can stop lecturing. Instead, they pivot their core identity to become dynamic academic facilitators. With the AI handling the initial introduction to the material, universities can aggressively repurpose the in-person class time that was previously spent on basic lectures. Students now dedicate their physical classroom hours exclusively to advanced collaborative problem-solving and highly complex peer-to-peer group projects. To monitor this process, faculty rely on formative analytics. Formative analytics is the practice of collecting real-time data on student performance during the learning process to adjust teaching strategies immediately. Looking at this digital dashboard, instructors can track the exact interactions between students and the AI. The analytics pinpoint precisely where individual students are hitting bottlenecks long before they ever walk into the physical classroom. This architecture uses AI as a tool for student engagement, necessitating a total redesign of traditional grading metrics and assessment strategies. For executives planning an implementation strategy, the most severe operational risk is faculty burnout during the transition phase. The first mandatory step in the blueprint is to run strictly isolated technology pilot tests before attempting any full curriculum integration. Universities also need comprehensive specialized staff training programs. These programs are required to safely transition instructors out of traditional lecturing and into their new facilitator roles. Leadership must accept a stark financial and temporal trade-off. They have to delay full institutional rollouts and dedicate real, immediate budget specifically to professional development. Investing heavily in faculty support and phased rollouts is the only guaranteed insurance policy against technological resistance and long-term initiative failure. For educational decision-makers, the ultimate return on investment from the Harvard framework is clear: higher student comprehension delivered in less time. This blueprint targets institutions willing to fund deep structural curricular redesign. Schools simply searching for a cheap, unvetted technological band-aid must actively avoid this approach. Ultimately, this kind of AI integration does not replace human educators. Instead, it exponentially increases the value of their in-person time. The reward for enduring this operational friction is a scalable, self-paced ecosystem designed to prioritize individual student mastery.